In the last couple of lectures, we have discussed one-dimensional signals, and in particular, we talked about pulse amplitude modulated signals, which is PAM signals, and we discussed these types of signals both in the baseband as well as in the bandpass. And we also saw that their geometric representation is one-dimensional. That means the points in the signal space lie on a single line. And in the last lecture, we also talked about how to construct orthogonal signals which are non-overlapping. So if you want to construct a set of, say, an n number of orthogonal signals over a duration t, we saw how we could construct them by having them as non-overlapping signals over the duration t. All right. Let us today extend our discussion to two-dimensional signals. And we are going to talk about two-dimensional signals both in the baseband as well as in the bandpass today. And we are going to see how we can construct not just binary signals in two-dimensional, but also emery signals in two dimensions. And we will do so for both baseband as well as for bandpass. Now, in the process, we are going to also discuss a few things regarding the geometric representation using the basis functions. And one of the important things that we are going to understand today is the fact that the geometric representation using basis functions or orthonormal basis functions does not depend on the choice of basis functions. So we can have different sets of basis functions to represent the same signals, and the representation may differ in terms of the visual appearance, because the axis would become different, that is, the basis functions would be different. However, the characteristics of the signals themselves would remain unchanged. That means irrespective of the choice of the basis functions, the signals characteristics will remain unaltered as long as we have the basis functions with the properties of being orthonormal. So let's look at the first case where we have a set of two signals, S1 of t and S2 of t, and as you can see, they have overlap in the duration t. So S1 of t and S2 of t both are defined in the duration 0 to t. So these are overlapping signals. And if you take the dot product between these two signals, you will also notice that they are orthogonal to each other. What we will first do is we will first show that the dot product is indeed 0. Okay, again, I'm not going to go through that explanation. You should all know how to calculate the dot product between two signals, and clearly the dot product between them is 0. That means they are orthogonal. Now we can compute the basis functions for these signals using the Gram-Schmidt orthogonalization procedure, and based on the basis functions, we can represent these signals in the vector space as the geometric representation. So if we calculate the basis functions phi1 of t and phi2 of t, we will have a certain representation. So to calculate phi1 of t, we first compute g1 of t, which is the intermediate function, and from g1 of t we can calculate the first basis function phi1 as g1 of t divided by the norm of g1 of t. And how to calculate g1 of t? It's by this expression, as we are familiar from the Gram-Schmidt procedure. So when we compute the denominator term here, the norm, we get it as the square root of the energy of the signal S1 of t, and then we can compute the energy of the signal S1 of t, which we call as E1, and we get that as A root t. So from that, we now have our first basis function phi1 of t defined as the signal S1 of t divided by the square root of its energy. So we have the first basis function as this form over here, okay, which is plotted over here. Okay, so that's our first basis function. Now the energy of the basis function, just to verify that this basis function has satisfies the property of being unit energy. So if you calculate the energy of this basis function, we see that it is indeed equal to 1. So that means this has unit energy. Next, we will calculate the second basis function phi 2 of t by first computing the intermediate function g2 of t by this expression, which we are all familiar with from the Gram-Schmidt procedure once again. And so we get g2 of t as this form, s2 of t minus s21 phi 1 of t. So we need to first calculate what is s21. s21 is nothing but the projection of the signal s2 of t onto the basis function phi 1 of t. So we know phi 1 of t already, which we have calculated. So we can now compute s21, and we find that s21 turns out to be 0. So that means the projection of the signal s2 of t onto the basis function phi 1 of t is 0, or in other words, it means that s2 of t is perpendicular to phi 1 of t. So that means s2 of t lies on its basis function itself. So what we notice is the intermediate function g2 of t turns out to be only s2 of t, and from that we have computed the second basis function phi 2 of t, and since phi 2 of t is orthogonal to phi 1 of t, and since s21 is also 0, so we conclude that the signal s2 of t actually lies on the basis function phi 2 of t itself. Okay, so so we have the general form of phi 2 of t as the signal s2 of t divided by its norm, and to compute the norm we first compute the energy of s2 of t and then take the square root. So we get the norm of s2 of t, and from that we now compute the second basis function phi 2 of t, which we get as follows. So because s2 of t is defined as having a value of a from 0 to t by 2, and then as minus a from t by 2 to t, so we have two different values in this range. So we have this phi 2 of t defined as such. Okay, so that's our second basis function phi 2 of t, and again we can verify that phi 2 of t also has unit energy by computing its energy, and as we see here, the energy is equal to 1, confirming that as should be the property of the basis function, it indeed has unit energy. And next we can also verify that phi 1 of t and phi 2 of t, that is the two basis functions, are indeed orthogonal to each other. So we can compute the dot product between those two and verify that it is equal to 0. So that means since it's equal to 0, the basis functions are orthogonal to each other, and as we have seen earlier, they are both having unit energy. So these are orthonormal basis functions. Okay, so since we have now only two signals, we have already computed two basis signals, basis functions. So the basis functions is always less than or equal to the total number of signals. So in this case, two signals, and we already have two basis functions, so that would be sufficient, and sufficient to represent the two signals. Now we can get the vector representation of the two signals s1 of t and s2 of t as the general form of the equation, s1 of t as s11 phi 1 and plus s12 phi 2. So where s11 is the projection of s1 of t onto phi 1 of t, and s1 of t s12 is the projection of s1 onto the basis function phi 2, and so on, right? So we have the vector notation for these signals as the elements s11 s12, and similarly for the signal s2 of t as s21 s22. So we can compute what is s11 s12, which are basically projections of s1 onto the basis functions phi 1 and phi 2 respectively. So as we see here, s11 is basically the norm of the signal, so we get that as a root t, and s12 in this case turns out to be 0. Obviously that should be the case, because since s1 of t is lying on the basis function phi 1, its projection onto the second basis function should be 0. Okay, so we have the vector representation of the signal s1 of t as such. So we have the projection of s1 onto the basis function phi 1, which is its norm a root t, and the projection of the basis function onto the second basis function is 0 because it lies on the basis function itself. Okay, so next we can represent the second signal S2 of t using its projection onto the correspond to the individual basis functions. So S21 we already calculated earlier and we got that as 0, and so the projection of S2 of t onto the basis function phi1 is 0 since the signal S2 of t lies on the basis function phi2 of t, and correspondingly the projection of S2 of t onto the basis function phi2 of t, which is S22, turns out to be its norm, as it should be the case. So we have the vector representation of S2 of t as 0, root of its energy, okay, or its norm. So we have now the vector representations of the two signals S1 of t and S2 of t, and as we have both the signals to be of equal energy, so energy E1 and E2 both, as we saw earlier, they computed as A root 2, so we can simply write that as E, right? The energy for both is same, and we can now plot them in the geometric representation in the vector space. So signal S1 is lying on the basis function phi1 with the norm, that is the distance from the origin, being square root of E, and its y-axis value, that is the value for phi2, is 0 because it's lying on the phi1 axis. Similarly, the point for the second signal S2 is 0 root E. So we have this representation for the two signals, and what we notice here is that in the geometric representation we can clearly see that these two signal vectors, so if we have the signal vector S1 as in this direction and the signal vector for S2 as this, then we clearly see that the angle between them is 90 degrees. So they are perpendicular to each other. That means they are orthogonal to each other, which is what we had proved earlier, right at the beginning, that S1 and S2 of t are overlapping signals but orthogonal with respect to each other. So we can clearly see that orthogonality in the geometric representation as well. So the signal vectors are perpendicular to each other. Next, we can also calculate the distance between the two signals, okay, the Euclidean distance between the two, and from the general representation, as we have discussed previously, we can calculate the distance between 2 points, and from this diagram we can actually compute this distance between S1 and S2 simply by using Pythagoras theorem, since that forms a right angle triangle, right? So the distance turns out to be square root of 2e, right? So that's the distance between these 2 points S1 and S2. Okay, now to summarize all of this, we see that the signals S1 and S2 are overlapping signals over the interval 0 to t, and they are orthogonal with respect to each other, but they are not unit energy. Okay, the signals S1 and S2 themselves are not unit energy signals, but the basis functions that we constructed using these signals are orthogonal as well as unit energy, but the signals themselves are not unit energy. Okay, so once we obtain the basis functions which are orthogonal as well as orthonormal, we got the geometric representation of the signals. Okay, so that's the general procedure which we are all familiar with. Okay, how to get the geometric representation of signals in terms of the basis functions, and we can clearly get a lot of information related to the signals in terms of the angle between them, or in terms of the distance between the signals, and so on, in an intuitive way once we have the geometric representation. The next part of the discussion that we are going to see is that these properties of the signals in terms of the energy of the signal, or the norm of the signal, or the distance between the two signals, or the angle between the two signals, right? These characteristics of the signals will remain unchanged even if we represent those signals using a different set of basis functions. So we have these basis functions phi1 and phi2 of t, right? Phi1 of t and phi2 of t. So now instead of using this particular phi1 and phi2 of t that we calculated earlier, we can compute a different set of basis functions using a completely different set of signals, and then use those basis functions to represent our original signals S1 and S2. So now what we have here is we have two signals which are non-overlapping over the interval 0 to t. So we have this S1 of t which is defined in the interval 0 to t by 2, and the S2 of t is defined in the interval t by 2 to t. And this is something which we saw in the last lecture, right? How to have non-overlapping signals which are orthogonal to each other, and we discussed this in detail in our previous lecture, and how to construct m such signals. So this is the example for two signals, and using these two signals we will calculate a set of basis functions, and using those basis functions we will represent our original signals S1 and S2. So these non-overlapping signals, we call them as S1 dash and S2 dash. The earlier signals that we saw, those are S1 and S2 of t, right? So using these non-overlapping signals S1 dash and S2 dash, we are going to compute their basis functions, which we again which we'll call as phi1 of t and phi2 of t. Again, we are going to use the Gram-Schmidt procedure to do that, and basically I'm going to run through this very quickly because you should be familiar with the Gram-Schmidt procedure by now. So let's quickly run through that, and then represent the signals using those new basis functions, and see whether the original properties or characteristics of the signals S1 and S2 are preserved even while representing them using a different set of basis functions. Okay, so let's first verify that what's the energies of the two signals S1 dash and S2 dash, and as you can see, both those signals S1 dash and S2 dash have the same energy, which is equal to a squared t, or the norms of the two signals is a root t, which is the same as we had earlier as well for the other signals. Okay, now using the Gram-Schmidt procedure, we can calculate phi1 of t as S1 of t by the norm of S1 of t, and similarly phi2 of t as S2 of t by the norm of S2 of t. Since S1 and S2 again are orthogonal with respect to each other by virtue of them being non-overlapping, we have the basis functions as the signals themselves divided by their norms. So this is one simplistic idea that you should have in mind. When the signals themselves are orthogonal, then the intermediate functions will be equal to the signals itself. Okay, so when you're using Gram-Schmidt procedure, don't waste your time calculating the intermediate functions if you can verify the fact that the signals are orthogonal with respect to each other. So the intermediate function for computing the first basis function is the same as the S1 or signal S1 of t, and the intermediate function for the second basis function is the same as the second signal S2 of t, and from this we get phi1 of t and phi2 of t as these values, root 2 by t over these intervals, right? So clearly these basis functions phi1 and phi2 that we have here are different from the basis functions that we computed earlier. So if you recall, the earlier basis functions were, where is that phi1? So this was phi2 of t, and the corresponding phi1 of t is over here, right? And if you see the new ones that we have constructed now using the non-overlapping signals, these have a completely different amplitude and completely different intervals. So we have them as a different set of basis functions. What we will now do is we will represent our original signals S1 of t and S2 of t using these newly computed basis functions phi1 and phi2, which are computed or obtained using the non-overlapping signals S1 dash and S2 dash. Okay, so once we have computed the basis functions, we can again verify that these basis functions are orthonormal by checking that they have unit energy, and also that they are orthogonal to each other, and that is verified over here. Again, you can do these calculations for yourself and verify those properties. Okay, so now what we're going to do is we will represent our original signals S1 of t and S2 of t using these new basis functions. And for that to have the vector representation in terms of these new basis functions, we have to compute the projection of S1 of t onto this new basis function phi1 of t. Similarly, the projection of S1 of t onto the new basis function phi2 of t. So we get S11 and S12. Similarly, we can compute S21 and S22 and get the vector representation of the signals. So clearly now we have S11 and S12. If you recall, in the previous case we got S12 as 0, but now S12 is non-zero, so we have S11 to have a certain value and S12 also has a certain value. And similarly we can have S21 and S22 as well. We have computed the computed S21 and S22 by taking the dot product between S2 and phi1 and S2 and phi2 respectively, right? So we get these values for these projections. So using these projections, we can now represent our signals S1 of t and S2 of t in terms of their vector notation S1 and S2 by these values that we have computed. Okay, this is the projection of S1 onto the new basis function phi1, the projection of S1 onto the new basis function phi2, and so on. So when we plot these points in the signal space with phi1 as one of the axis and the second basis function phi2 as the other axis, so we have S1 as a root t by 2, a root t by 2. So it is this particular point over here at 45 degrees between phi1 and phi2. So it's like point 1 comma 1 or 2 comma 2, right? It's the same value for the x and y coordinates. So we have this value for the signal, this representation for the signal S1. Similarly, we have the representation for the signal S2, which is a root t by 2 and minus a root t by 2, which is the x-axis value is positive and the y-axis value is negative, so that turns out to be a point over here. So we have this as 45 degrees between phi1 and phi2, but in the negative direction. Okay, so we have these two signals S1 and S2 with a completely different geometric representation, because phi1 and phi2 are now different. They are not the same phi1 and phi2 which we had earlier. For the previous case of phi1 and phi2, these points were lying on the axis, right, on the x-axis and y-axis. Now we have them on the plane between the axis, okay, in the space between the axis. And what we notice here is that even though we are representing these signals S1 and S2 using a completely different set of basis functions, their characteristics are totally preserved. So if you compute the energy of this signals, it will be the square of this term plus the square of this term, right? It will be a squared t by 2 plus a squared t by 2. That will be equal to a squared t, which is the energy of the signal S1. Similarly, the energy of the signal S2 is also a squared t. So we see that even though we are representing the signal using a different set of basis functions and we get a different representation in the vector space, the energies are still the same. So that means the energy property of the signal is preserved, which should be the case, because irrespective of how we represent the signal, the energy should not change, right? The next thing is we can also compute the distance between these two signals, okay, between these 2 points, and verify that we get the same answer which we got earlier. And the answer was the distance between the 2 points was root 2e earlier. We get the same value over here as well. So if you compute the distance between these 2 points with d, that is equal to root 2e, which is the same distance we had in the previous case as well. So even though we are using a different set of basis functions now, the distance between the two signals is still the same. So that is also preserved. And thirdly, we also notice that the angle between the two signals is still 90 degrees. So you see here, it's this forms a right angle triangle over here, right? So the angle between the two signals S1 and S2 is still 90 degrees. So the signals are still orthogonal. So what we conclude from this is that the geometric representation of the signals is invariant to the choice of the basis functions. That means irrespective of how we construct our basis functions, the representation of the signals should not be affected. That means the characteristics of the signals will remain unaltered. Okay, so we have seen this case for two signals, S1 and S2. Now we can extend this idea to a set of M signals, because when we talk about M-array signaling, where we will combine multiple bits to represent signals, we need multiple signals to represent each of those combinations. So instead of two signals, if we have a certain number, capital M number of signals, which is defined as 2 power k, where k is the number of bits per signal. So if each signal represents 2 bits, then we have 2 power 2, that is 4 different signals, because with 2 bits we can have 4 combinations, which is 0 0 0 1 1 0 1 1, and for each combination we need to have a separate signal to represent that combination. So therefore there should be 4 different signals for this particular case. And similarly, if we have 3 bits, that is k equal to 3, then we need to have we will have 8 different combinations, and that means we need 8 different signals to represent each of those combinations. Okay, so let's see how we can construct M-array signals using just 2 basis functions. So we have already seen how to have 2 signals with 2 basis functions. We will just extend the idea from this representation, either from this representation or from the earlier representation where we had the signals on the axis itself. So this representation over here. So using either this or our second notation, where the signals were at an angle of 45 degrees between the 2 axes, we can now construct 4 signals. So a simple way of doing that is to simply create the negative version of each of these signals. So for the signal S1, which we had earlier, we create a negative version of the signal S1 as minus S1. So it is diametrically opposite to the signal S1. That means it is at 180 degrees angle from the signal S1. So if this is root E and 0, the coordinates for the negative value is minus root E and 0. Similarly, for corresponding to the signal S2, we can create its negative equivalent or its negative version, which is diametrically opposite to it. So from 0 root E, we will have it as 0 negative root E. Okay, so we have these 2 signals S1 and S2 along with their negative counterparts minus S1 and minus S2. So now what we get is we have 4 different signals which are represented using 2 basis functions phi1 and phi2. Now S1 and S2 are orthogonal to each other. Minus S1 and minus S2 are also orthogonal to each other. S1 and minus S1, they are not orthogonal to each other because they are diametrically opposite. Their angle between them is 180 degrees. Similarly, the angle between S2 and minus S2 is 180 degrees. So we cannot say that all these 4 signals are mutually orthogonal, but they are orthogonal in pairs. S1 and S2 is orthogonal. Minus S1 and minus S2 is orthogonal with respect to each other, and similarly minus S1 is orthogonal to S2 and S1 is orthogonal to minus S2 and so on, but they are not all mutually orthogonal. Okay, mutually orthogonal means every combination should be orthogonal. In this case, that is not the case, because S1 and minus S1, S2 and minus S2, they are not orthogonal with respect to each other. But nonetheless, we are not interested in constructing just orthogonal signals. Okay, we can have orthogonal basis functions, but the signals not necessarily be orthogonal. So, okay, we just have a set of 4 signals now to represent MRE signaling with m equal to 4 using two basis functions phi1 and phi2. So we are seeing how to construct four signals using two basis functions in an easy way. Okay, so we have these four signals over here. Similarly, corresponding to the second representation of two signals S1 and S2, we have the corresponding negative versions of S1 and S2. So the negative version of S1 is minus S1 and the negative version of S2 is diametrically opposite to it, which is minus S2. And correspondingly, the X and Y axis values, as you can see, you will just have the signs changed appropriately. Okay, just note the fact that here, okay, there's a mistake over here. Please make a correction. This should be negative a root t by 2. So the y-axis value here, so it should be minus a root t by 2. Okay, so I missed a minus over here. Please make that correction. Okay, so we have now two versions of the constellation points for representing four signals using two basis functions. Okay, so we have done so, or we have created these four signals from our original two signals by taking their negative equivalents. Okay, so we have taken the negative of S1 and S2 as minus S1 and minus S2 and put them onto the geometric space. So that now gives us a combination of four signals. Okay. Now, since we notice that all these signals are not mutually orthogonal with respect to each other, they are not mutually orthogonal with respect to each other, but we see that S1 and S2 are orthogonal, and minus S1 and minus S2 are orthogonal, and hence we say that this set of signals is a bi-orthogonal set. It's not mutually orthogonal, or it's not a completely orthogonal set. It is a bi-orthogonal set. That means certain pairs are orthogonal. You have two pairs, S1 and S2 orthogonal, and minus S1 and minus S2 orthogonal with respect to each other. Okay, so we call this as bi-orthogonal set. Now, just as we constructed four signals from the original two signals to get MRE signal with m equal to 4, similarly, we can now extend this to construct a set of 8 signals using these same two basis functions phi1 and phi2. So we have S1, S2, minus S1, minus S2, these four signals which are lying on the axis, okay, on the axis of phi1 and phi2. And then we have the second representation where the points lie 45 degrees between the two axes, okay? And we can basically combine these two representations. So I can take this representation which lie on the axis and this representation where the signals lie at 45 degrees between the axes, and combine the two to get a set of 8 signals, and that will give us an MRE signal with m equal to 8. So this can be used to represent 8 different binary combinations where each combination is having a length of 3. So 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on up to 1, 1, 1, right? So when we have a set of 3 bits grouped together, we can have 8 possible combinations, and each combination has to be represented by a corresponding signal. And now we have 8 different signals, as you can see here. So 4 of the signals are lying on the axis and 4 of the signals are lying at 45 degrees between the axis. So we now have 8 different signals. Okay, now what we notice here is that all these 8 signals have the same distance from the origin. So the distance from the origin is root e, which is the norm of the signals. And since all these signals have the same distance, that means they lie on a circle of a certain radius which is equal to the norm of the signal, which is root e in this case, the square root of energy, right? So that means all the signals have equal energy. Okay, signal S1, S1 dash, S2, S2 dash, and so on. All the signals have equal energy, and one way to intuitively see that all the signals have equal energy is the fact that they are all lying on a circle. Okay, so that clearly tells us that the distance from the origin for each of those signal points is the same. That means all the signals have equal energy. We can also construct signals which need not have equal energy. Okay, in this particular case, all the signals have the same distance from the origin, or their norms are same. That means they have equal energy. That is not a necessity. We can also construct a set of 8 signals with different values of energy. So we will see how to do that. So if we have the geometric representation of the signals in a two-dimensional plane with two basis functions, that is phi1 and phi2, we can have 4 signals which lie on a particular on a circle of a certain radius root e1, and 4 other signals which lie on a different circle, on a circle of a different radius, that is where the distance is root e2. So now we have 8 signals in all. So that's signal number 1, signal number 2, so that's signal number 2 over here, signal number 3 and 4, and that's 5, 6, 7, 8, right? So we have these 8 signals. 4 of the signals are on a circle of radius root e1, and the other 4 are on a circle of radius root e2. So that means the signals on this first circle have an energy value of e1, and the signals on this second circle have an energy value of e2. And clearly the energy E2 is greater than the energy E1. So we now have biorthogonal signals. Okay, there are 4 biorthogonal signals with energy E1, and there are 4 biorthogonal signals with energy E2. So we have a set of 8 signals where we have lifted the restriction that the signals be of equal energy. So we no longer have all the signals of equal energy. But in this first example, what we see is that while these signals, while these signals on this line over here, they do not have equal energy, they do have equal phase. So the angle of this signal, the angle between this signal and this second signal on the outer circle, the angle between them is 0. Similarly, the angles between the signals over here is 0, and so on. So the only way to differentiate or distinguish these signals is by observing their amplitude. So if it's this amplitude, I identify it as a certain signal S1. If it is a different amplitude on that axis, it's phi2, and so on, right? Another way of doing that is we can have these constellations rotated with respect to each other. So now we can have the first constellation where the energy of the signals is E1, but the signals are lying on the basis function. So we have the first set of 4 signals with a certain energy E1, and they are lying on the basis functions phi1 and phi2 respectively, right? And so that's signal S1 and signal S2, the corresponding negative versions of those signals. And the second set of 4 signals, we can have them not on the axis but at 45 degrees between the axis. Okay, so now we have these angles, these signals, these 4 signals. So now what we notice is it's a combination of amplitude and phase now. So these signals have this point is having a certain energy and a certain angle with respect to the basis function, but the other signal, it's having a different energy and a different angle with respect to the basis function as well. So it's a combination of amplitude as well as phase. Okay, and what we see in practice is that this constellation, the second constellation, where we have the signals arranged such that they are different in their energy as well as in their angle, is a better representation when we are going to transmit these signals over an additive white Gaussian noise channels, because when we transmit this signal, the channel adds noise, and therefore the signal will get shifted depending on how much noise is getting added. It will get shifted to a different point, and we want to ensure that the error remains as small as possible at the receiver side. And clearly this representation is better because if this point gets shifted to a different place because of noise, it will still be far away from the other point to avoid any confusion and making any error. But if you see in this particular case, the distance between these 2 points is so small that a small amount of noise can push it in the vicinity of this point, and the receiver can wrongly interpret this signal as the outer signal, right? So it can cause an error. So based on that, the second constellation that we have here, which has a combination of amplitude and phase values, is a better constellation and preferable for a communication over an additive wide Gaussian noise channel, because that would give us a lower bit error rate. Okay, so what we have seen so far is the representation of two-dimensional signals for different values of m. We started with m equal to 2, which is binary representation, and then we saw how we could extend those signals in a two-dimensional space to have m equal to 4 signals as well as m equal to 8 signals. And then we also saw how we can have constellations where the signals are not necessarily having equal energy, but we also saw how we can arrange the signals to have different energies as well as different phase angles. Okay, so that's the overall discussion to now. And the important point that we need to remember here is that when we represent signals using basis functions, irrespective of the choice of the basis functions, the characteristics of the signal will not get altered. Okay, the energy, for example, the norm of the signal, the distance between the signal points, all of these, as well as the angle between the signals, right? All of these will remain preserved irrespective of the choice of the basis functions. Now let us take our discussion to investigate two-dimensional representation of signals in the bandpass. So we'll see how we can represent bandpass signals in 2 dimension, and we'll see different types of modulations in the process, and we'll also see their mathematical as well as their geometric representations. Okay, so let us move on to 2-dimensional bandpass signals over here. And in this discussion, we are going to restrict ourselves to baseband signals which have equal energy. So we'll start off with baseband signals which have equal energy, and then use these signals to modulate a carrier signal to produce the bandpass versions of the baseband signals. Okay, so all the signals have equal energy. So if we represent the baseband signals as Sm of t using some pulse g of t, so g of t is an arbitrary pulse of some arbitrary shape, and the g of t itself is having a normalized amplitude of 1, and so therefore when we want to transmit g of t for different signals or to represent different signals, each of the signals will have a certain amplitude am. But since we are going to choose all the signals to have equal energy, all the AMs should be the same. So A1, A2, A3 and so on should all be the same. So we simply call it as AG of t because they are all going to have equal energy. And for simplicity, we will also make that value of A equal to 1. So the signal Sm of t for all the m's is simply going to be g of t. Okay, so now that's the bandpass pulse. All the signals have the same amplitude, and all the pulses have the same amplitude, representing each of the m signals. Okay, now from these baseband signals, we can transform or convert them to the corresponding bandpass equivalents by multiplying the baseband signal with a carrier signal of some frequency fc, where the value of fc is very high. Okay, so we have corresponding to each of the baseband signals S1 of t, S2 of t, S3 of t and so on, a corresponding bandpass signal which we will denote as V1 of t, V2 of t and so on. So in general we simply call it as Vm of t equals Sm of t multiplied with the carrier for the value of m going from 1 to capital M. Okay, and of course each of these signals Sm of t is defined in the interval 0 to t, so the corresponding bandpass signals are also defined in that same interval. Okay, so now if we calculate the energy of these bandpass signals, so the energy of the bandpass signals is simply going to be this v square of t over the interval 0 to t. This is something which we have done a couple of lectures back. Okay, a similar calculation we have done when we did one-dimensional PAM signals. When we calculated the energy of PAM signals in one dimension and computed the energy, we had an integral of a similar kind. And basically, what happens is this is a carrier signal of twice the carrier frequency, right? The cosine wave of frequency 2fc, and this is the baseband signal. Okay, so the amplitude of this is going to be unchanged when this cosine 2 pi fct is very large, right? So when this is 2 fct over one cycle, the amplitude will not change much, so the average over one cycle is going to be 0. So this integral will effectively turn out to be 0. Again, refer to a couple of lectures back where we have discussed something similar when we are dealing with bandpass PAM signals. So I'm not going to repeat that process over here. So the second integral turns out to be 0. So that leaves us with only this first integral, which is basically the energy of the baseband signal. Okay, so half multiplied with the energy of the baseband signal. So this is again a result that we have seen earlier when we were discussing bandpass PAM signals, and the fact is that the bandpass signal energy is half the baseband signal energy. So the energy of the signal in the bandpass is half the energy of the signal in the baseband, which is something which we have seen earlier a couple of lectures back. Okay, so this is what we have mentioned here. The second integral turns out to be 0. Okay, so now if we call, since we choose all the baseband signals, EMs, to have the same energy, which we'll call as E, the corresponding bandpass signals, EVs, also will have the same energies corresponding for the different V's, right? So because each of the baseband signals is having the same energy. So after modulation, that is multiplying with the sinusoidal function of frequency fc, all the bandpass signals will also have the same energy, okay, which we will simply denote as ES, okay, for our purposes for now. So once we have all the bandpass signals with a certain energy ES, we can now represent them in their geometric representation using the basis functions in two dimensions, that is with two basis functions. So we can have a set of 4 bandpass signals where you can have the constellation points either on the basis functions or at 45 degrees. So I've shown the example here for 45 degrees, but the norm over here is now root ES rather than root E, okay, not the baseband energy, but it is square root of ES, which is the energy of the bandpass signals, which is basically going to be 50% of the energy of the baseband signals. Okay, similarly, we also have a set of 8 signals. So this is a constellation with 8 signals in 2 dimensions. And again, what we have here is each of these constellation points having the same distance root ES from the origin, which is nothing but the norm. Okay, again, what we notice here is that all the 4 signals or the 8 signals, they all have equal energy, and therefore they all will have equal amplitude. The only difference between these signals is the angle. So we can generate these signals by simply modifying the angle of the carrier signal. So we are multiplying the signal with the carrier signal, and since the only distinction between the signals is the phase angle of the bandpass signal, so we can simply represent each of the bandpass signals as the baseband signal multiplied with a carrier of a certain phase shift. So with m equal to 4, we need 4 different phase angles. For m equal to 8, we will need 8 different phase angles, and so on. So in general, what we see is that the phase shifts are the angle between the signals is represented by phase shifts which are multiples of 2 pi by m. So if I have four signals, the angle between them is 2 pi by 4, which is pi by 2. So if you notice, the angle between any two signals is 90 degrees when I have four signals, and if there are 8 signals, the angle between them will be 2 pi by 8, which is pi by 4. Okay, each signal, okay, the angle between any two signals here is 45 degrees, which is pi by 4, and so on. So in general, when we have signals with equal energies in the baseband, the corresponding bandpass equivalents also will have equal energies. So the corresponding bandpass signals simply can be thought of as the baseband signals multiplying the carriers of a certain frequency and a certain phase shift. So the phase shift theta m determines the signal point in the constellation over here. So depending on the value of m, that is the number of signals we need, we can create that many phase angles. For m equal to 4, we have 4 different phase angles. For m equal to 8, we have 8 different phase angles, and so on. So the general notation to calculate the phase angles is theta m, which is given by this expression. And the choice of this capital N can either be 0 or 1. And as we will see later, you can choose either 0 or 1, doesn't matter. But if we compare to n equal to 0, when we choose n equal to 1, what we will see is that the constellation points will simply be rotated by a certain amount. Okay, we will come to that later. So let us simply look at the representation now. So we are going to have this signal Sm of t, which is nothing but our baseband signal AMG of t, and since we are choosing all the baseband signals to have equal energy, that means they all have equal amplitude, so we will have them as A. And since we have chosen A as equal to 1 for simplicity, so our baseband signal is simply our baseband pulse of unit amplitude, okay, normalized to be unit amplitude, right, G of t. So this G of t is multiplying this cosine 2 pi fct plus theta m, so that gives us our bandpass signals. Okay, so we have our bandpass signals Vm of t, where each Vm of t is having a certain angle theta m. So what we notice is that this particular representation distinguishes the signals only based on their phase angles. The only thing that that differs among all the m signals is the value of the angle theta m. Everything else is the same, right? If you see these parameters, nothing else has changed except for theta m, for m equal to 1 to capital M. So such a modulation scheme where the information is contained in the phase angle of the carrier signal is called as the carrier phase modulated signals. And as I said earlier, we can choose the value of n equal to 0 or 1, it doesn't matter. If we choose 0, we get a certain constellation, and if we choose n equal to 1, we get a different constellation. But if you compare the two constellations, you will notice that the second constellation is a rotated version of the first constellation. Okay, and how much is the rotation? The rotation is pi by m. So compared to this constellation, and the constellation on the right hand side is rotated by an angle of pi by 4. Since we have m equal to 4 here, it's rotated by pi by 4. Okay, so this constellation, if you rotate it by pi by 4, which is 90 degrees, you get this constellation on the right hand side. So the constellation for n equal to 1 can be obtained by rotating the constellation for n equal to 0 by an angle of pi by m in general, in this case pi by 4. Okay, and that is what we have mentioned over here. Okay, now a special case of this carrier phase modulated signal is when we have the pulse shape G of t as a rectangular pulse. Okay, we started with G of t as some arbitrary pulse shape, not necessarily a rectangular pulse shape. But if the pulse shape is rectangular and it has a certain energy Eg, then what happens is the rectangular pulse has the energy Eg uniformly distributed over the interval t. So over the interval t, the energy is uniformly distributed because the amplitude is the same over the entire duration t. So we can represent the amplitude of the signal as the square root of the energy divided by t, because the energy is uniformly distributed over the entire duration of the pulse. So this is the case for a rectangular pulse. Okay, normally for any arbitrary pulse shape that is not the case, but for rectangular pulse this is an observation, right? A very straightforward observation that the energy is going to be uniformly distributed in the interval t. So the amplitude at any point of time will be the energy at that time divided by t under the root. Okay, now since we know that the relationship between the energy of the baseband signal and the bandpass signal, the bandpass signal energy is half the energy of the baseband, or equivalently the baseband energy is 2 times the bandpass energy, right? So we can write this baseband energy Eg as 2 times the bandpass energy Es. So we have this g of t as square root of 2 Es by t over the interval 0 to t. So the energy is basically uniformly distributed in the interval 0 to t when the pulse shape is rectangular. Okay, in that case we can have our modulated signal of this form, where the g of t is now having a value of square root of 2 Es by t, or simply square root of Eg by t over the interval 0 to t, and multiplied with the carrier signal of a certain phase theta m. So v1 of t has a phase angle theta 1, v2 of t has a phase angle theta 2, and so on up to all the m signals. Now we have a total of m different angles, so we can either start from 0 and go to m minus 1, or start from 1 and go up to m. So when m is 0 we call it as theta 0, and so on. Okay, so the counting for m, you can have it from 0 to m minus 1 or 1 to m, it does not matter. Okay, it's just notational, so you can figure it out and make sense of it. Okay, so we now have our bandpass signal Vm of t of this form. Okay, so this form of the bandpass signal, which is obtained by using a rectangular pulse shape for g of t, where we get this amplitude as you being uniformly, the energy being uniformly distributed in the interval 0 to t. This form of bandpass signal is called as phase shift keying signal. Okay, PSK signal. So this is called as it is a form of digital phase modulation called as phase shift keying, or PSK. Okay, so in general when we say PSK, it applies to binary PSK, but that means for m equal to 2, capital M equal to 2, there are two signals, the V1 and V2, or V0 and V1. And then if we have m equal to 4, we will have 4 signals, in which case we will call it as QPSK signals, or quadrature phase shift keying signals. So the carrier phase modulated signal that we get by using a rectangular pulse is a special case of the carrier phase modulation, which we call as phase shift keying. Okay, so for m equal to 2, we will have binary phase shift keying, or BPSK signal, and for m equal to 4, we have what is called as QPSK signal, or quadrature phase shift keying signals. And similarly for m equal to 8, we will have what is called as 8 PSK signals, and so on. So now why do we call this as a quadrature phase shift keying signal? So we can understand that by looking at our general expression for the bandpass signal. Okay, so the general expression is the baseband pulse of unit amplitude, or and each of the signals, each of the representations have the same energy, and multiplied with the carrier of a certain frequency, high frequency, and a certain phase angle theta m. Now if we simplify this using the trigonometric identity cosine A plus B, which is cosine A cosine B minus sine A sine B, we get this form. And clearly in this expression, g of t is our pulse, which is the baseband pulse of unit amplitude, Cosine theta m and sine theta m are simply going to be some numbers depending on the value of theta that we have. Cosine theta will be a certain number and sine theta will be a certain number. So this number, it's not a function of time, so we'll simply call cosine theta as AMC. That means the amplitude of the cosine component, that multiplies g of t, and AMS will be the the amplitude corresponding to the sine component that multiplies g of t. So we have AMC as cosine theta m and AMS as sine theta m. So we just substitute that in our expression. So what we see is that our PSK waveform, which has information contained in the angle theta, is now seen to be as a sum of two signals which have a certain amplitude, AMS and AMC and AMS. But the difference is that it is sum of two quadrature signals, cosine and sine. Okay, and in fact minus sign, you can call it as minus sign and take these amplitudes as positive. So we have the PSK signal, or the phase shift keyed signal, represented in terms of two signals, cosine and sine, which are called as quadrature signals. Clearly we are familiar that cosine and sine are orthogonal with respect to each other, because the angle between cosine and sine is 90 degrees, and similarly the angle between cosine and minus sine is also 90 degrees. So we call them as two quadrature carriers. So the PSK signal is a sum of two quadrature carriers which have an amplitude modulation associated with them. So the sine component is having an amplitude modulation AMS, and the cosine component is having an amplitude modulation AMC, so corresponding to the value of m, A1, A2, A3, and so on, right? So we have these two as quadrature components which are orthogonal with respect to each other, and the cosine component has an amplitude g of t multiplied with AMC, and the sine component, which is minus sine component, has an amplitude g of t AMS. Okay, so by expanding the expression for the PSK signal using our trigonometric identity, we get a better insight into how the signal can be visualized. So we can see that it is a sum of two quadrature carriers which have been amplitude modulated. So they have their amplitudes g of t AMC and g of t AMS respectively. Now, since we started off with the baseband signals to have, for all the baseband signals to have equal energy, the corresponding bandpass signals also will have equal energy. But this notation is telling us that the cosine component is having a certain amplitude where g of t is multiplied with AMC. So corresponding to V1 of t, it will be A1C, corresponding to V2 of t, it will be A2C, and so on. Similarly, corresponding to V1 and V2 and so on, it will be A1S, A2S, and so on. That multiplies the sine component, right? So if you want to have the geometric representation of this signal in the two-dimensional space, so we can have the representation based on the quadrature carrier notation for the PSK waveform. The original energy is root ES, and it's getting multiplied with a factor cosine theta m, which we call as AMC, because g of t, okay, after modulation will have an energy of ES, so its norm will be root ES, and that gets multiplied with AMC, which is nothing but cosine theta m. Similarly, the other component on this minus sign, it will have a multiplying factor of sine theta m, which is AMS, right? So the vector notation in the two-dimensional space will have, for each of the signals S1, S2, S3, and so on, the original energy root ES, which is equal energy for all these signals, multiplied by this factor cosine theta m. Okay, so these will be the points in the two-dimensional space which will have a certain angle cosine theta m or multiplying factor cosine theta m and sine theta m, depending on the angle theta m itself. Now we can calculate what these values will be and see what the constellation of the signals will look like in the geometric representation for different values of m. So again, we know from our earlier discussion that theta m can be given by this expression, and we can choose the value of n as either 0 or 1. So let's choose either 0 or 1. So we'll start with 0. When we make n equal to 0, we get the theta m as simply 2 pi small m by capital M. And that gives us our signal representation as a square root of es multiplied with this cosine term and square root of es multiplied with this sine term. So now when we put m equal to 4, we can get the different thetas: theta 0, theta 1, theta 2, theta 3. And so there are 4 different phase angles corresponding for different values of m. So when you put this will be cosine 0, so root es cosine 0 and root es sine 0, so we get this point in space. Similarly, the second signal, which we call as s1, will be given by this notation. So we have the vector representations of all the 4 signals corresponding to n equal to 0, and we can plot these points in the 2-dimensional space. So the first point is root es0, which is here. The second point is 0 root es, which is lying on the y-axis. The third point is negative root es0, which is diametrically opposite to the first signal. And the fourth point is diametrically opposite to the second signal, right? So we have this constellation for the bandpass signals of 4 signals, or which is called as the QPSK signal, quadrature phase shift keyed signals, QPSK signal. And similarly, we can have the constellation for binary PSK, which is for m equal to 2. And again, we can choose n equal to 0 or 1. So we have chosen n equal to 0 here, and we get the 2 phase angles as 0 and pi. So that's 0 degrees and 180 degrees. If we had chosen n equal to 1, those points will be pi by 2 and 3 pi by 2. So the points would have lied on the y-axis, okay, on the second basis function. Either way, we get the same characteristics for the signals. Okay, so we have the constellations. We can construct the constellations as we prefer to have them. So as we have said earlier also, by setting n equal to 1, what happens is the constellation gets rotated by pi by m. So in the binary case, if we set n equal to 1, the points will lie on the y-axis. That means this constellation will get rotated by 90 degrees, which is pi by 2, m equal to 2. Similarly, if we have the constellation for m equal to 4, using the choice of n equal to 1, we will have these points rotated by 45 degrees. So it will be, the points will lie over here. Okay. So that's just an aside which you can visualize for yourself. Now the next thing that we are going to do is we are going to calculate the basis functions for these bandpass representations. So for the PSK signal, which is the bandpass signal, we want to compute the basis functions. And rather than going through the Gram-Schmidt procedure, we are going to just use the fact that the signals are actually composed of the components cosine and sine, which are orthogonal to each other, which we saw earlier, right? So we have these signals orthogonal with respect to each other. So using that fact, we can simply calculate the basis functions phi1 and phi2 as simply each of those quadrature components divided by their norms. So we have the first component, which we call as the in phase component, or simply vi of t. So I stands for in phase component, and generally the cosine component is called as the in phase component, and the sine component is called as the quadrature component. So the quadrature component we denote it as vq of t. So the first basis function, phi1 of t, will be the in phase component divided by its norm. Again, we are using the fact that if the signals are composed of are composed in such a way that they are orthogonal with respect to each other, then the basis function will simply be computed using the intermediate functions, and the intermediate functions will simply be the individual signals themselves. So g1 of t will be s1 of t, g2 of t will be s2 of t, and so on. So phi1 of t will be vi of t, the first component, phi 2 of t will be simply the second signal, which is the sine component, and so on, right? So phi 1 of t will be the in-phase component divided by its norm. So the in-phase component is this, and divided by the norm. To compute the norm of the signal, we will first find its energy and then take the square root of the energy, right? Again, when we take this integral, we can, using the trigonometric identity, it will split into two integrals. I'm not going to do that working. We've done it earlier also, and we've done it a couple of lectures back also during the PAM discussion. So the second integral will become 0 because it will have a term corresponding to 2fc, right? So using that, we eventually get the energy value as this, and we take the square root of the energy, so that gives us the norm of the signal. Okay, how to compute that, I'm going to leave that to you, and we have already done it a couple of times already, so you should be able to work it out yourself. So that's the energy of the signal and the corresponding norm. So from that, we can calculate the first basis function, which is the in-phase component vi of t, which is this term, divided by its norm, which we have over here. Okay, so that's our first basis function for the bandpass representation of the PSK signal. And similarly, we can compute the second basis function using the quadrature component vq of t. The quadrature component is where is that? The quadrature component is minus g of t ams sine 2 pi fct. So again, the second basis function will be the quadrature component divided by its norm. Again, when you calculate the norm for the quadrature component, we calculate first its energy and then take the square root of the energy to get the norm. And again, we don't really have to calculate this because between the in-phase component and the quadrature component, the only change is the angle between them. So if we change the angle, the energy should not necessarily change, right? So a phase shift will not alter the energy. So the energy for the quadrature component is going to be the same as the energy of the in-phase component. So we'll have the same notation, right? So just as we had here, AMC AG by 2, and so we ended up with this, the AMC anyway cancels out. Similarly, for the quadrature component, we'll have it in this form, and the AMS and AMS will cancel out, so we end up getting this as our second basis function. Okay, so next we can compute the Euclidean distance between the signal points. If you have two signals, you can compute the distance between S1 and S2. In general, if you have a certain set of M signals, we can calculate the distance between each pair of points SM and SN. So the distance between 2 points SM and SN is the square root of the difference between the difference, square root of the norm of the difference, right? Squared. So the general expression, if we work it out, again, I'm not going to go through the proof of this, okay? The general expression for the distance between any 2 points in the signal space constellation is given by this expression in terms of the bandpass energy ES. So if I want to compute the energy between S1 and S2, just put the value of M and N as 1 and 2, and we will get the distance between signal numbers 1 and 2 and so on. Okay, so if you want to calculate the distance between S1 and S0, so you put M equal to 1 and 0. Okay, so M and N. So we get the distance as 2 root ES in this particular case. Okay, and clearly this is the distance from the constellation. So the distance between 2 points for M equal to 2 for the binary case, the points are lying on a straight line with the distance of root ES on either side of the origin. So the distance between the points is 2 root ES. So let us quickly verify that. So if you look at these points here, for the binary case M equal to 2, the distance between the two constellation points is 2 root ES. So from here, from the origin, one point is to the right at a distance of ES, root ES. The other point is to the left by a distance of root ES. So the total distance between the two is 2 times root ES. So which is exactly what we get from this expression. And similarly, we can compute the distance between any 2 points for any constellation, for any value of m, that is. Okay. So one of the points of interest for us is the minimum Euclidean distance. So if we have a set of points in the geometric representation representing the m different signals, certain signals may be far away from each other and certain signals may be close to each other. So for example, if you look at the case for m equal to 4, the distance between these two signals is different than the distance between these two signals, right? So we want to calculate in a given constellation what is the minimum distance between any two signal points. Okay, the smallest distance between signal points, and that smallest distance has an effect on the error probability of the communication. So because when we have the signals being transmitted over a communication channel, then the noise will shift the points to a different place. So if 2 points are very close to each other, it is highly likely that one point gets interpreted as the other point in the signal space, leading to an error. So the minimum Euclidean distance is a parameter of interest for us because that has a direct effect on the performance of the receiver in terms of the bit error rate when we have communication over a communication channel that has noise. Okay, so the minimum Euclidean distance will occur when the 2 points are adjacent to each other. Okay, so Sm and Sm minus 1 or Sm and Sm plus 1. So the 2 points which are next to each other, those will have the smallest distance between them, and this has an effect on the error performance of the receiver. So we can calculate the minimum distance using the same formula by choosing two consecutive values of m, and this does have an effect on the error performance of the signal, or rather we should say on the error performance of the receiver. Okay. So when we design our signals in the signal space, we need to arrange the signal points in such a way that the minimum distance between the signals is as high as possible. If we get two signal points which are very close to each other, the chance of one signal being interpreted as a different signal because of noise becomes high, and that increases the probability of error in the communication system. So it is essential that we design our signals in the constellation in an appropriate way depending on our channel conditions. Now, so far we have been talking about two-dimensional bandpass signals where the energy of the signals are all equal. All the signals have equal energy. So that means all the signals in the constellation lie on a circle, right? But we can release this restriction and to consider the case where the bandpass signals have unequal energies. Okay, in that case, what we have is a different form of bandpass signals, giving rise to a different form of modulation called as quadrature amplitude modulation. In PSK, which is phase shift keying signals, each signal point is having a different phase, and depending on the number of points we have, each signal point is representing a certain number of bits. For example, if there are 4 points as in QPSK, then we have each signal point representing 2 bits of information. If there are 8 points, then each signal point is representing 3 bits of information, and so on. All the information about these 3 bits or 2 bits is contained in general in the k bits is contained in the phase angle of the signal, and the energy or amplitude of the signal is going to remain unchanged. For the amplitudes of all the signals are remaining the same, so there is no information contained in the amplitudes themselves. So the entire information is contained in the phase angle of the signals. Now, when we look at signals which have unequal energies, that means the signals will have different amplitudes. Each of the signals may have different amplitudes and phases, or a combination of both. and this gives rise to a different type of digital modulation called as quadrature amplitude modulation. So basically in QAM we remove the restriction that all the signals have equal energy, so that means they are no longer located on a circle of a certain radius. Okay, so that is the difference between QAM and PSK and QAM. Okay, again in QAM we can have different levels of QAM, like 4 QAM, which we simply call as QAM, and we can have 16 QAM, 32 QAM, and so on and so forth. Okay, so from our general notation for the bandpass signal, we had we had two quadrature carriers, right? We have a cosine term and a sine term. Now in QAM what we do is we choose PAM signal, and that PAM signal modulates the cosine term and sine term separately. So if we have, say, a PAM signal, a binary PAM signal, that means the binary PAM signal has two amplitudes, A1 and A2. So these two amplitude levels will modulate the cosine component, and the same two amplitude levels, okay, A1 and A2, will modulate the sine component. So we have a combination of these two quadrature components with modulations A1 and A2 separately, right? So what happens is we can have the cosine component modulated by a PAM level A1, and the sine component modulated by the same A1. So that's one combination. Or we can have A1 for the first and A2 for the sine component, or A2 for the cosine component and A1 for the first component, or A2 for both. So that gives us 4 different combinations, right? So the information is now not just contained in the phase but also in the amplitude. So that's why we call it as quadrature amplitude modulation. Now the constellation, since it's no longer equal energy signals, so the constellation will no longer be a circular constellation where the constellation points are joined by a circle as in PSK. In contrast, the constellations for QAM signals are square constellations or rectangular constellations. Okay, so they will be joined by a rectangular shape. Okay, so basically what happens in QAM is that the two quadrature components, cosine and sine, as I mentioned earlier, are each modulated separately by a different PAM signal. Okay, so we have a binary PAM signal, for example, modulating the cosine component, and a binary PAM signal modulating the sine component. So there are two parallel streams of data, or in case of binary, two parallel bit streams containing zeros and ones. So one of the bit stream is modulating the cosine component, and the other bit stream is modulating the sine component. So in the first stream we can have 0, and the second stream the bit may be 0. Or we can have the first stream with the bit value of 0 and the second stream with the bit value of 1. Or we can have the third combination where the first stream has a bit value of 1 and the second stream 0, or the fourth combination where both the bit values are 1, right? So the two PAM signals, okay, are modulating the two quadrature carriers separately in parallel. So that gives rise to 4 different combinations, okay, and this is what we call as quadrature amplitude modulation, or 4 QAM. Generally when it's 4, we don't usually write it as 4 QAM, we simply write it as QAM. So by default when we write QAM, it automatically means 4 QAM. Okay, so if each of the quadrature carriers is modulated with the binary PAM signal, then we get a quadrature amplitude modulated signal, or 4 QAM to be precise. Okay, so we have the two quadrature components, cosine and sine, and we can have the cosine modulated with a component which we simply call it A1C and A2C, and the sine component modulated with the A1S and A2S. So depending on these combinations, we can have 4 possible combinations. So we can have A1C, A1S, A1C, A2S, A2C, A1S, and A2C, A2S, right? So 4 different combinations. So that gives rise to 4 points in the constellation. And now, because these need not be of equal energy, okay, in this case, since the distance from the origin is the same for all the 4 points, for the QAM signal of 4 QAM, they turn out to be of equal energy. But as we see later, when we increase the value of m to 16 or 32, we will end up in a scenario where the energies are not the same. Okay, so if we modulate the quadrature carriers, cosine and sine, using a binary PAM signal, then we get a QAM signal. Okay, so as I mentioned earlier, so we have these 4 different combinations. So each combination gives rise to a particular symbol. So we have 4 combinations of 4 symbols, so that gives us 4 constellation points or 4 different signals to represent each of the 4 signals, to represent each of the 4 symbols, that is. Okay, so similarly, instead of modulating each of these quadrature carriers, cosine and sine, using a binary PAM, instead if we use a 4 PAM signal as our baseband signal to modulate this cosine and sine components, then we will get a 16 QAM constellation. That means with 4 PAM we have 16 possible combinations, because each PAM has 4 voltage levels. So 4 voltage levels modulating the cosine component and 4 voltage levels modulating the sine component in parallel. So when we combine them together, we can have with these 16 different combinations. So it's like having 4 bits combined together, and 4 bits combined together will give us 16 different combinations. So with that we will have what is called as 16 QAM, and the constellation of the 16 QAM is going to appear as follows. So we have 16 different points, and clearly we see that now the energies of these signals are no longer the same. So the energy of this signal and the energy of this signal and the energy of this signal, so they're all different. Okay, certain points may have same energies, but not all the points have the same energies, right? So the energy of this and this is same because they have the same distance, same norm values, but the energy of this and this is different. These two have the same energy, but they are different from this and different from this, and so on. So all the signals are no longer having the same energy. So we have this case where we have the rectangular constellation because the signals are no longer are having the same norm value, so we cannot simply represent them on a circle. Okay, when we have them on the circle, that means all of them have the same amplitude, which in turn means that all of them have the same energy. Okay, in the case of QAM, that is not the case. So when each of the 2 quadrature carriers, cosine term and the sine term, are getting modulated by 4 PAM signal, that gives us 16 different combinations or 16 constellation points, which we call as the 16 QAM signal. So we will have the general form of the QAM waveform, okay, just as we had earlier for the PSK signals. So we have the cosine component and the sine component, and we have the baseband pulse GM of t multiplied with the AMC component, okay, because each of these AMC and AMS represents the PAM amplitudes that are going to influence the modulation. Okay, so we will have different combinations of these. So if we have 4 signals here, that will give rise to 16 combinations. If this M has only 2 possible values, that will give rise to 4 combinations, and so on. So the maximum value of M here, which is capital M, denotes the M PAM. Okay, so this capital M here denotes the PAM signal, not the 16 that you see here. Okay, this is the output now in terms of the number of constellation points, but this capital M here is determined by the number of input combinations, which is the baseband combinations, which is the PAM signals. Okay, so be careful when you are talking about this particular notation for QAM. So this capital M here denotes the PAM signals that are modulating these quadrature carriers. Okay, so we have this general notation for the QAM waveforms, and from that we can write it in a slightly different way. So if you recall, if you look at this constellation point, we can see that these constellation points are a combinations of amplitude variations as well as phase variations. So if you look at these points which are lying on the same line, they have the same phase angle, but they have different amplitudes. If you look at this point and this point, okay, these two, they have the same amplitudes but different phase angles. And similarly, if you look at this point and this point, they have same amplitudes but different angles and so on, right? So we can represent our QAM waveforms as a combination of amplitude and phase modulations. So QAM can be thought of as a combination of amplitude and phase modulations. So we can represent this in terms of AMG of t. So that's an amplitude modulating term and a phase modulating term. Okay, so we have AMs where M goes from 1 to M1. So there are M1 different amplitudes, and theta n's where n goes from 1 to m2. So the number of phase angles available to us is m2, okay, capital M2. So if you see here, the number of amplitude levels, so that's one amplitude, then that's a second amplitude, then we have a third amplitude, that's also the same amplitude. So that line and that line is going to be same length. So in one quadrant there are three different amplitudes. In this quadrant there are three different amplitudes. In this quadrant there are three different amplitudes. In this quadrant there are three different amplitudes, right? So if you just take their magnitudes, basically there are three different energy levels or three different norms for this particular 16 constellation points. And similarly, if we look at the angles, so we have a certain angle for these 2 points, an angle for this point, and an angle for this point. So these 4 points in this quadrant have three different angles, and then there are three different angles over here, three different angles over here, three different angles over here. So we have a certain number of angles and a certain number of magnitudes. So M1 denotes all the possible number of amplitudes or the distinct amplitudes available for our constellation points, and M2 denotes the distinct phase angles for our constellation points. So the total number of constellation points that we can have in this case is going to be the product of M1 and M2. So the number of distinct signals that we can create in the constellation is M1 into M2. Okay, now in terms of the number of the symbols itself, each signal point is representing a specific symbol. So that means the number of symbols that we are transmitting is equal to M1 into M2. And we can have a relationship between the number of symbols and the number of bits. So since each symbol is going to have logarithm to the base 2 M1 M2 bits, okay, generally if there are 4 different symbols, that means there are 2 bits per symbol. If there are 8 different symbols, there are 3 bits per symbol, right? So the general relationship between the number of symbols and the number of bits is that the number of bits is equal to logarithm to the base 2 of the number of symbols. So if the number of symbols is M1 into M2, then the number of bits is logarithm to the base 2 of M1 into M2. So from that we can also calculate the bit rate of the system. So if the symbol rate is denoted as RS, then the bit rate can be calculated as RS into the number of the bits per symbol, right? So or vice versa, we can calculate the symbol rate from the bit rate as the bit rate divided by the number of bits per symbol. Okay, so log 2 M1 M2 is the number of bits per symbol. So the symbol rate is the bit rate divided by the number of bits per symbol, or the bit rate will be the symbol rate multiplied by the number of bits per symbol. So to conclude, we can think of the quadrature amplitude modulation as in 2 forms. First, we can think of it as 2 quadrature carriers being modulated by by parallel streams of parallel PAM signals. So a PAM signal modulating the cosine component and a PAM signal modulating the sine component in parallel, and it will give us a certain number of combinations. Or we can also look at the QAM signal as a combination of amplitude and phase modulation. So we have an amplitude modulation aspect in the expression and a phase modulation aspect or component in the expression. So we can write it in terms of amplitude and phase modulation. So we have two representations for the QAM signal as we see here. So the first representation over here is in terms of parallel MPAM modulations, and the second representation is as a combination of amplitude and phase modulation. So we have an amplitude modulation, so each of the M amplitude levels and each of the M2 phase levels. Okay, so now if you talk about the energy of the bandpass QAM signal, so if you look at the bandpass pulse itself, okay, g of t cosine 2 pi f ct and g of t sine 2 pi f ct, that is going to be ES. Okay, so its norm is going to be root ES. But what happens is each constellation point is further having an amplitude modulation associated with it. So we have this root ES getting multiplied with AMC and AMS respectively. So each constellation point can be represented in terms of these points as root ES into AMC and root ES into AMS. You can have the signal space representation in a two-dimensional space. That means in terms of two basis functions. We can represent the QAM signal in this form as we have shown here. Okay, root ES AMC. AMC is the amplitude modulation component with the cosine term, and AMS is the amplitude modulation component with the sine term, and that will give us the signal space representation of the QAM signals in the geometric representation, that is. Okay, so from this we can now calculate the energy of the cosine component and the sine component. So the energy of the cosine component is simply going to be AM square AMC square ES, so basically the square of this term, and the energy of the sine component is going to be the square of this term. Okay, so the norms is what is represented. Okay, the points in the space are representing the norms, and that is the coordinates of the axis, the x-axis and y-axis, or the coordinates of the corresponding basis functions, that is. Okay, so we have the energies of each of the components, quadrature components. So the energy of the cosine component and the energy of the sine component will be the energy, the square of this multiplied with the energy of g of t, which is ES, right? So we have the energies of each of those components given here, and extending these ideas we can build bigger constellations. So just as we had for m equal to 4, we can extend it to 8 and 16 and 32 and 64 and so on. So we can have this QAM representation as parallel streams of MPAM signals modulating the quadrature carriers cosine and sine, in which case we have this sort of constellations, which is the rectangular constellation. Or we can think of the QAM signals as a combination of MPAM and PSK. So that means it's a combination of amplitude and phase modulations. So in that case we can have the constellations looking in this form, okay, where we can have them joined by the circular constellations. But of course there are multiple circles of different radii. That means all the signals have different energy. Okay, and finally a last point of observation is that we can calculate the energy of each of the COM signals, which is simply the square of the norm. And so the average energy of the signal will be the energy of each signal added together divided by the total number of signals, which is m signals. So that should give us the average energies of the QAM signals. Okay, so what we have seen today in this lecture is a representation of 2D signals in baseband as well as bandpass. And to summarize, one of the important things that we discussed in the first part of the lecture was the fact that the choice of the basis functions does not affect the characteristics of the signal. So the signal's characteristics remain intact even if you use a different set of basis functions. Just the representation becomes different. And then we looked into the bandpass representation of signals in 2 dimensions, that is using 2 basis functions. And we talked in particular where the signals had equal energy, in which case we got the PSK signals. And when we remove that restriction that the energies need not be the same, we ended up with a different version called as Quadrature amplitude modulation. Okay, even within PSK, we could have constructed signals with different energies as well, but where we have a combination of phase as well as amplitude, which effectively leads us to quadrature amplitude modulation. Okay, so in general we have the quadrature amplitude modulation where signals have unequal energy, but in phase shift keying the signals have equal energy. That means they all lie on all the signal points lie on a circle, so we have circular constellations. And in the case of QAM signals, we have rectangular constellations. Again, the interpretation and visualization can be different. So we can think of the QAM signal as 2 quadrature carriers, cosine and sine, being modulated parallelly by 2 different data streams. Or we can think of the quadrature amplitude modulation QAM signal as combined amplitude and phase modulation, giving rise to multiple combinations of amplitudes and phases. So we can distinguish the signals based on each of their amplitudes and phase values. So that's one aspect of it. And another aspect we talked about was the PSK signal also can be thought of as being a sum of 2 quadrature carriers being amplitude modulated. Okay, so that's by using some basic math, we can visualize the signals in a specific way and have a better or more meaningful interpretation of these signals. A key constraint here is that when we design our signals, we want to make sure that the minimum distance between the constellation points is as large as possible, because otherwise that will increase the bit error rate in the communication system. And however, there are no requirements. If you want to transmit at a faster rate, we want to increase the value of m. If we increase the value of m, we are going to end up with points getting, the constellation points getting closer to each other. And that would have, that means if the points are closer to each other, the effects of channel impairments will be more severe, resulting in more errors at the receiver side. So depending on the requirements, we have to design the signal properly and make a balance between the data rate that we need to achieve and the bit error probability that is required for a certain application. Okay, so we have talked about 2-dimensional signals in both baseband as well as in bandpass today, and in the process we have discussed different types of modulation. Okay, previously we had talked about only pulse amplitude modulation as 1-dimensional baseband and bandpass signals, and now we have talked about PSK waveforms, carrier phase modulated signals, and PSK waveforms and QAM waveforms for bandpass representations in 2 dimensions.